Okay, now I'd like to tell you about the law of Biot-Savart. I don't think you pronounce the T actually. It's the law of Biot-Savart, or the magnetic field due to a current element. Okay, calculating the magnetic field due to a current element, you would use the law of Biot-Savart. Okay, so a current element. First of all, what is a current element? This is just one segment of a wire. Imagine that there's a whole bunch of wire going this way. So you got the whole wire going that way. But we're going to just look at one segment. And the segment we're going to have is going to be infinitesimally small. So we're going to call that length DL. Now I had to draw it big so that you could see it. But it's really going to be, when we do the math for this, we're going to assume that DL is really tiny, infinitesimally tiny. Now the current is heading this way, and let's just say it's heading straight down the way. And the current is I. Turns out that if you want to figure out the magnetic field due to this, just to this little current element, well, if you want to know it here, then you go from the center of your DL, you draw a vector R, and let's see, which way is it going to be heading? It's going to be heading, the field is going to be heading straight up. Yeah, that's right, straight up. And let's call this angle theta. The angle between the direction of DL. DL, we're going to call it, that's going to be a vector. It's going to be pointing in the same direction as I. So I need to sneak a vector sign in there for DL. Okay. Now to get the field just due to this little DL is really tiny. And so to remind ourselves that this is a field not for the whole wire, but just for DL, I'm going to put the field there. It's not a big field, it's a little field. It's dB field. Okay? So the dB, the little field, the very tiny, tiny field due to this little DL is going to equal, it's going to look very similar to the equation from the last video. It's going to be mu naught over 4 pi. Remember, this whole thing equals 1 times 10 to the negative 7th. And the units on that are Teslas, meters over amps. So I'll write that here. Mu naught over 4 pi. That's going to be 1 times 10 to the negative 7th. And the units on that is Teslas, meters over amps. And you'll see why that has to be Teslas and meters over amps in a little bit. A different video, actually. Okay, so this is mu naught over 4 pi. And then times I times dl cross r, or we can say I dl sine of theta all over r squared. So this looks a lot like qv sine of theta over r squared, except we're going to have the I times dl times the sine of theta over r squared. There's a cross product in here. You could say it's I dl, that vector, cross r, and then you would have an r cubed down here. Another way to do that also is to use a unit vector, and I won't go into that, but maybe your book has I dl cross a unit vector, and the unit vector has a magnitude of 1, so that's why that's still just r squared down here. Okay, well, in any case, the magnetic field due to this current element is going to be just a constant times how big the current is times dl times the sine of theta, the angle that it makes, all over r squared, r being the distance from the center of the dl to where you want to find the field. Okay, so let me show you how this works for a long wire, a chart, the magnetic field due to a long line of current going. Let's have the wire be going this way. So here's a wire, and it's infinitely long both ways. And I'm going to put a coordinate system on here. There we are. And let's say we want to know the field due to this wire. And let's say this distance from here to there is a distance a away from the wire. And let's say the current is heading up. So the I is up. That's the I. And right now I know that the field, the direction of the field right there is going to be into the page. So if I put a compass right here, if I put a compass there, it's going to point down. If I put a compass on this side, it will point up. Okay, but I'd like to know what the field is there, the strength of the field. Okay, so I'm going to make a little dl, and I'm going to find the field due to that little dl. That field due to that little dl is this. I'm going to make a little dl. That's a little arrow I drew there. It's hey, I know I call it dl, but because I'm in the y direction, how about I call that dy? And this is down here, a distance of y down here. So it's down a distance y from the origin, and it's the thickness of this little bit of wire is dy, or the height of that wire is dy. Okay, well, the r is this vector. And so to get the field due to that, it's going to be mu naught over 4 pi, just a constant. And now I'm going to do I times dl, but I changed the dl to dy since it's in the y direction. I times dy times the sine of theta all over the r squared. Okay, now I'm going to add up then for every circuit, for every current element, that each one of these has some effect on the field there. And so what I'm going to do is I'm going to just add them all up with an integral. But there's a problem when I do that. When I go to integrate this, you see how my differential is dy? But what else is changing? Depending on where I go, the theta changes. So if I'm right here, theta is 90 degrees. But if I'm down here, theta is smaller. So theta is changing. And so is r. R, how far away this is from the point I want, is changing. So I have a variable in r, a variable in theta, and my differentials in dy. So this is a problem. Okay, well, what we do is we're just going to put everything in terms of y. So I can put theta in terms of y, and I can put r squared in terms of y. It turns out that before I integrate, I'm going to do this. So bring this over. Use I. I is just a constant. It's a number that would be 4 amps or 1 amp or what have you. I'll have a dy there. But to get r squared, if I'd like to get r squared in terms of y, you see if this is r, that I can put that in terms of y with the Pythagorean theorem. Turns out that r is going to be equal to the square root of y squared plus a squared. And when I square that, I get this. So I just get that. And the theta, the sine of theta, is the opposite side over the adjacent side, or the hypotenuse. So sine of theta is the opposite side, a, over the hypotenuse, and the hypotenuse is r again. So it's going to be r squared plus a squared. This time I have to square root it. There's no square root here because remember we square that r. Okay, well, it turns out then that I can combine these a little bit. And so dB is equal to mu naught over 4 pi. And then I'm going to have I dy a just being a constant. And then this can combine to y squared plus a squared to the 3/2 power. Okay, now I don't want just the field just due to this current element. So to get the field due to all of them, I'm going to sum up with an integral. I'm going to pull out all the constants. Mu naught I a over 4 pi. And I'm going to sum up the dy over y squared plus a squared to the 3/2 power. And I'm going to start at in y equals negative infinity, and I'm not going to stop summing those to y equals infinity. Okay, when you do that integral, I'll tell you what you get in the next video. So when you do this integral, I'll tell you what you get. Okay, I'll see you.